All right, today we want to look at circles and inscribed angles. So we have a little bit of definitions we need to go over, in particular what an inscribed angle is. So an inscribed angle I would draw like this. This is an example of an inscribed angle. So if you look at that, one thing we notice is that the vertex of the angle is on the circle itself. So an inscribed angle has its vertex on the circle. And then if you think about its sides right here, its sides are chords of the circle. Okay. And its sides are chords of the circle. So that is what an inscribed angle is. We could draw lots and lots and lots of them. So this is an inscribed angle, and this is an inscribed angle. Okay, so some of them are big, some of them are small. The only requirement is that the vertex is on the circle and the sides are chords of the circle. Okay, so we have several different theorems about these inscribed angles. So the first one is that the measure of an inscribed angle is equal to half the measure of its intercepted arc. So let's draw a picture of this and visualize what this is saying. So let's say we have this angle, let's call it angle LMN. Okay, so if I were to look at the measure of this inscribed angle, whose vertex is on the circle, so angle LMN, that its measure would be half of this arc that it intercepts. So it goes from L to N. That is the intercepted arc. So this is the intercepted arc. So here the measure of angle M would be half the measure of arc LN. Okay, and of course we're not talking about length, we're talking about measure in degrees. Okay, so if you think about it, if we were to draw the central angle in right there, the central angle is exactly equal to the measure of LN. And hopefully you can see that it's pretty obvious that LMN is smaller than that central angle. Okay, in fact, it's exactly half as large. Okay, so it's fairly intuitive that it's smaller, and perhaps not so intuitive that it's half of it, but indeed it is half. Okay. Our next theorem is that if an inscribed angle intercepts a semicircle, then it's a right angle, and this follows directly from the theorem above. So if you think about a semicircle would have its ends on a diameter. Okay, so this part would be a semicircle. It would have to be having its endpoints on a diameter. So if there is an angle that's inscribed and it intercepts that, okay, so let's say it's right here, and it intercepts that, or it could be right here and it intercepts that, or it could be right here and it intercepts that. No matter where it is, okay, we're going to get a right angle. Okay, well, the measure of a semicircle is 180 degrees. And because we have that these angles intercept that arc that is 180 degrees, these angles will all be half of that. So this is half of 180, which is 90. This is half of 180, which is 90. This is 1/2. It doesn't matter where the angle is, regardless of where it is, it will always be a right angle because it's intercepting an arc of 180 degrees and its measure is half of that. It's 90. Okay. So let's look at a few examples of using these theorems. So we want to find the measures of angles 1, 2, and 3 in this diagram. Okay, so one thing to notice first is that we have a diameter right here, and so that angle 3 intercepts a semicircle. And so that means that the measure of angle 3 is going to have to be half of that semicircle, half of that 180 or 90 degrees, plus we know, because it intercepts the semicircle, that it's a right angle from this theorem. Okay, so that one's 90 degrees. Okay, so that takes care of angle 3. Now, could we figure out angle 1 or angle 2? Well, we do have this 108 degrees. That's this arc from here to here. And that arc is intercepted by angle 1. And so we know that the measure of angle 1 is half of its intercepted arc, or half the measure of, well, I guess it's not named. I'll just say half of the 108 degrees. Okay, so the measure of angle 1 has to be 54. Okay, so we now have 90 and 54. And so that should be enough to help us know that angle 2 then, because it's in a triangle, angles 1, 2, and 3 have to add up to 180. So the measure of angle 2 is going to be 36 degrees, so that they will all add up to 180. Okay. All right, let's look at the picture on the bottom. All right, we need to find the measure of angle ABC, that's this angle, and the measure of arc BD, that's this arc. Okay. So we know that the measure of angle ABC is half of its intercepted arc, which is arc AC. Okay, and so that's half of, we know that that is 72. So this one has to be 36 degrees. And then if we look at measure of angle BD, well, that's intercepted by BCD. So the measure of angle BCD has to be half of its measure of its intercepted arc, which is the measure of angle BD. Well, what we know this time is that BCD is 28, so 28 is half of the measure that we're looking for. Multiply both sides by 2, and we'll get that 56 degrees is the measure of angle BD. Okay, so these theorems can, of course, be used to find out the measure of an angle if you know the measure of an arc, and they can be used to find the measure of an intercepted arc if you know the measure of the included or the inscribed angle. Okay. Our next theorem, if two inscribed angles intercept the same arc, they have to be congruent. Hopefully this is pretty intuitive. So let's say I had an arc AB, and I had this angle that intercepted AB, and I had this angle that intercepted AB. Okay. Well, this measure is half of arc AB. This one is half of AB, and so by the transitive property, these have to be exactly the same, right? Okay, so we could write out a formal proof for that, but probably you can just follow the argument in your head, and we don't need to write down the whole proof, but that's the way that the proof would go. Okay, so no matter, I could put another one over here, or I could put the angle right here, okay? No matter where the angle is, they all, if they intercept the same arc, all of those are half of AB, so they all have to be exactly the same. They have to be congruent. Okay. The next one, well, this one is worthy of proof. It's not quite as easy. I mean, you might be able to see it, but we're still going to go ahead and prove it. So in this one, we have a quadrilateral that's inscribed in a circle. So let me just draw sort of a random quadrilateral. I'll call it A, B, C, D. Okay, so it's inscribed in a circle, so all of its vertices lie on the circle. And if that's true, then it has supplementary opposite angles. Okay, so in terms of what our picture is saying is, so we would, okay, so the given is that the quadrilateral ABC is inscribed in a circle, and then what we would have to prove is that if I took the measure of angle B and added the measure of angle D, that would be 180. So B and D that are opposite, those are supplementary. And then A and C are also opposite angles. Those are also supplementary. So the measure of angle A plus the measure of angle C would have to be 180 degrees. Okay. So how would we go about proving this? Let's see if we can fit it on here. Okay. All right, so we have that the ABCD is inscribed. Okay, so that's given. All right, so what we have is a bunch of different inscribed angles. So let's go ahead and just use our inscribed angle theorem and say, okay, well, the measure of angle A, what would that be? Okay, well, A intercepts arc BCD. Now, it's a major arc, so we would have to name it with 3. So it's going to be 1/2 the measure of arc BCD. Okay, so this is, okay, inscribed angle is half intercepted arc. And we know that it's an inscribed angle because the polygon is inscribed from number 1. Okay, and similarly, we could look at the measure of angle B. That's going to be half the measure of CDA. I'm just going to put ditto for this one. And then measure of angle C is going to be half the measure of, okay, and then this one looks like it's a minor arc, so we can call this one just DB. And then measure of angle D. Okay. And that's going to be 1/2 of the measure of its intercepted arc. Well, let's see. We assumed that that this one was a major arc, so this one must be minor. We'll just call that AC. It's hard to tell from my picture, I guess, but we'll just assume it is. All right. And so let's just go ahead and look at what happens when we add together the things that are in question. So measure of angle B plus the measure of angle D. Okay, well, if we added these two together, and because of space constraints, I'm just going to go ahead and add these and factor out the 1/2 all in one. So I'm going to get 1/2 the measure of CDA plus the measure of AC. Okay, so that is the addition property of equality as well as factoring. So I did that with, what was it, 3 and 5, right? Okay, and then if you look, the measure of CDA, so CDA right there, plus the measure of AC, well, that's the whole way around the circle. That's a full 360 degrees. Okay, and so the measure of angle B plus the measure of angle D is 1/2 of 360 degrees, which is equal to 180. And that's just by the arc addition postulate and simplification. Okay. And so that gives us angle B, the measure of angle B plus D is 180. I've run out of room, but you can see that we would do the same thing to show that A plus C is 180. So A would go for, we'd have from B, C, D plus C would be D back to B. That would be the whole entire circle, 360. Okay, so we would have 1/2 of 360 again, which is 180. So those would also add up to 180. All right. So let's go ahead and apply that theorem to this particular problem. So we want to find all the measures of the angles of this quadrilateral. So we're given 3 of them, or expressions for 3 of them. A is x plus 16, D is x plus 30, and angle C measures x minus 18. We're not sure what B is, so we'll have to eventually get to a place where we can figure that out. Okay, but we do know that because the quadrilateral is inscribed in a circle, that A and C are going to be supplementary, and B and D are going to be supplementary. Okay, now we don't know what B is. We don't have an expression for that. So at this point, it's not super useful or helpful until we actually know what D is. Then it will be useful. Right now, though, because we have expressions for both A and C, we know that if I took the measure of angle A, which is x plus 16, and added the measure of angle C, which is x minus 18, I would get 180 because those two are supplementary. Okay, so I have 2x minus 2 is 180, or 2x is 182, which means that x is 91 degrees. So that's helpful because now we know that the measure of angle A is 91 plus 16, or 107. We know that the measure of angle D is 91 plus 30, or 121. And we know that the measure of angle C is 91 minus 18, or 73. Okay. We can also verify that the 107 and 73 add up to 180. Those are supplementary, so that's always a good check. And we also know the angles B and D have to be supplementary. Since we know that the measure of angle D is 121, we know then that this has to be supplementary to it, so measure of angle B must be 59. So if we add up these two, we all get 180. Okay. All right. So those are the important theorems related to inscribed angles in triangles.